Hi, I'm Emily,
And I'm Alexi.
and we're presenting an underground mine plan for the Erinsbrook Deposit. The Erinsbrook Deposit is an iron oxide copper gold deposit with their primary commodities being copper and gold with traces of silver in the deposit. The grade of the copper and gold varies locally, but it's fairly consistent throughout the entire deposit. The ore body is 480 meters underground and it extends a length of 1,040 meters deep. It's composed of a brecciated granite complex which extends 680 by 750 meters laterally. The Erinsbrook deposit is located in Australia, and the specific location is flat with few trees and scrub vegetation, so an underground mine will minimally affect the area. The climate is hot and dry in the summer and cool to mild in the winter, which results in about 170 millimeters of rainfall each year.
In order to determine the mining method for Erinsbrook, the type of mining method had to be chosen. The mining method selected for the deposit was artificially supported. This is due to the strength of the hanging wall being 120 megapascals, mineralization, and the size of the ore body. The three artificially supported mining methods that were considered for the Erinsbrook deposit include cut and fill, drift and fill, and bench and fill. These fall under an ore body dip of 45 to 90 degrees. This is suitable for the Erinsbrook deposit as the ore body dips at 90 degrees. Cut and fill and drift and fill were eliminated for the Erinsbrook deposit due to being selective methods. Erinsbrook deposit would be better suited for a bulk mining method due to it being a massive deposit. Choosing a selective method would be impractical as the cost would be higher and the recovery would be low. The other method considered was bench and fill, which is a bulk mining method. Bench and fill requires the width of the ore body to be narrow or medium. The width of Erinsbrook ore body is massive, which doesn't meet the bench and fill requirement. The selected mining method for the Erinsbrook deposit is sublevel stoping. Sublevel stoping is an effective method for narrow to wide, steep dipping deposits. This makes it suitable for the steeply dipping vertical structures in the deposit.
The metal prices for the two primary commodities, copper and gold, were calculated as an average of the spot price, the 3-year trailing average, and the long-term historic average to give the most accurate prediction. The average copper price is $2.92 per pound. The average gold price is $43.70 per gram, which is equivalent to $1,359 per ton. The values given for the costs are expressed as NSR, so it's a fixed annual cost. The break-even cutoff NSR is the total of the mining, processing, transportation, and G&A costs, which is a total of $59.60 per ton. We assume that the mining cost for the sublevel stoping is $40 per ton, since the stopes used will be larger due to the size of the massive deposit. The internal cutoff NSR would be the total of the processing, transportation, and G&A costs, which is $19.60 per ton. By looking at the grade tonnage curve, you can see that there are about 60 million tons above the cutoff grade, and there's about $112 per ton average NSR above the cutoff.
The deposit will be mined such that the roof of the stope will be blasted and loose rocks or muck will fall through the drill ore pass. A load haul dump will transport the muck to an ore pass where it will fall through a hopper that feeds a crusher. The crushed muck will be then sent to a skip using a conveyor. Conveyors are efficient since they are only to be used up to a depth of 500 meters and a production rate of more than 5,000 tons per day. The production rate and depth of Erinsbrook deposit is too large to use ramp haulage. Using a vertical shaft hoist will be the most cost efficient as the deposit has 480 meters of overburden above it. Hoisting is essential for the operation, as it will be necessary to have means of transportation for workers and material underground. The machinery for the ore hoist is situated above the shaft, installed in the headframe. The ore will be then unloaded into a bin in the headframe and then transported by a belt conveyor to an intermediate storage. The ore is then transported on belt conveyors from the ore storage to the mineral processing facility. Once the stope is completely hollowed out, it is backfilled from the bottom up. The material of the backfill for this operation will be cemented rock fill and hydraulic fill made from the waste rock and tails produced from the mining operations. After blasting, Load haul dumps can drive in to load the muck and dump it at a nearby ore pass. The waste rock will go through a mineral processing treatment, and the tailings will be transported to another surface plant via pipelines. The rest of the hydraulic fill fraction will be reticulated in the form of slurry through pipelines to underground voids. The materials used for the backfill will have high strength to support the roof of the empty stope.
There are numerous mine infrastructure and services needed for the operation of the mine and for sublevel stoping to be used. Access and material transport is crucial to be able to drill and blast and extract the ore from the ground. This includes an access ramp, drifts, and a hoist system to be able to transport material, equipment, and employees to and from the surface. Ventilation is used to circulate air throughout the mine and maintain proper air quality. The intake and exhaust will be placed on the surface, and the fans will be placed underground. Electricity is required at the site to power all operations, including the processing plant, lighting, heating, and other functions. The electricity will be supplied to the site through power lines, assuming there is one close to the deposit. Surface water is required at the site for processing and treatment purposes, mostly for slurry transport and flotation. The surface water will be obtained from the groundwater at the deposit and recycled through the process. Compressed air will be used as an energy source for tunneling and drifting, operating slurry pumps, and ventilation. Compressed air will also supply air to crushers, grinders, and flotation cells in the plant. Some of the communication in the mine will include a mine phone, leaky feeder, and Wi-Fi. The communication will be powered by electricity or battery and be located throughout the mine. The dewatering infrastructure used to manage the water in the mine includes sumps and pumps, which will be strategically placed to areas where water accumulates.
This table displays a water balance that was compiled to estimate the dewatering needs of the mine, including managing the water intake, containing the water, and pumping it out. This water balance is feasible as the inflow equals the outflow. Using the stability graph method, it was determined that the hydraulic radius is 7.5 meters. This means that the maximum dimension that can be applied to the stope is 7.5 meters. Assuming a vertical stope wall is being evaluated, a 7.5 meter hydraulic radius corresponds to a sidewall which is 30 meters. At a sublevel of 30 meters, the maximum stope length is 30 meters.
This is a general diagram of the sublevel stoping method we plan to use on the ore body. Due to the massive size of the deposit, multiple elevations can be mined at once to maximize production and utilize more active draw points in the mine. The stopes will be backfilled once they've been mined to maintain support as mining continues. Minimal support is required due to the competent strength of the ore and waste material. The ore body will be divided into primary and secondary stopes. In this diagram, the pink stopes are the primary stopes and will be mined and backfilled first, and the sequence will continue upwards. As soon as the backfill has cured, the secondary stopes, which are the blue columns in the diagram, can be mined at the same time. This can occur at multiple elevations throughout the deposit.
Based on the production rate, 50 tons an hour from each stope needs to be mined. To meet this requirement, one long hole drill is needed per excavation. The load haul dump selected is the CAT R 1700G model, which has a capacity of 12 tons. Assuming two elevations are being mined simultaneously, 6,000 tons per day of ore must be mined from each elevation. Assuming 5 primary stopes are mined on each level at one time, to ensure the stability of the mine, 1,200 tons per day must be extracted from each stope. This is equivalent to 50 tons per hour from each stope. Using this production rate, the selected load haul dumps would have to make 5 trips in 1 hour to achieve the target production. To maximize the milling capacity and net present value, 12,000 tons of ore will be fed to the plant each day. This is an annual amount of 4.38 million tons, assuming the mine is operating 24 hours a day for 365 days of the year. If a similar production rate occurs each year, the life of the mine will be approximately 14 years. To optimize the production, primary and secondary stopes can be mined simultaneously. Once the backfill of the primary stopes has been cured, the secondary can be mined as it will be stable. Mining more stopes may be desired when the commodity price increases and the material can be stockpiled. Due to the massive size of the ore body, it is possible to have multiple stopes in the vertical and horizontal directions.
In conclusion, the iron oxide copper gold deposit will be mined using the sublevel stoping and backfill method. It's assumed that the mining method costs $40 per ton with a process and transport cost of approximately $18 per ton. The metal prices are $2.92 per pound for copper and $43.70 per gold. The stope design will be mined in simultaneous stages with the primary and secondary stopes, and multiple elevations will be mined at once in the deposit. The equipment used are load haul dumps and long hole drills. The life of the mine is expected to be 14 years and will be optimized mining primary and secondary stopes at the same time.
Thank you so much for listening.
Please leave any questions or comments you have about our mine plan.